Hello, and welcome to episode 3 in a beginner's guide to EV conversions. I'm Richard with EV4U Custom Conversions. And in this episode, we're going to discuss which cells to use, how many cells, how are they wired. Remember we talked about series and parallel in the last episode. And we're going to discuss how all of the components are interrelated, nominal voltage, minimum voltage, maximum voltage of the cells, and much more. So let's get started. So I mentioned here's where things get interesting. We're starting to talk a little more about specifics, and this is where that interrelated aspect comes in. And what I mean by things are, interrelated, that relationship between components, meaning that the battery package voltage needs to match that of the motor, the controller, the charger, the DC to DC converter, your heating and AC systems. So, these answers will determine a lot as we go forward. Now, to answer these questions, which cells to use? Well, you have a lot of options today, and I'm not here to tell you which ones, but I'm going to tell you which ones we're going to use in this guide so that we have continuity throughout. And we're going to use, as I mentioned before, lithium iron phosphate cells. And so from here on out, when we refer to voltages and so forth, nominal, maximum, whatever, we're going to be referring to lithium iron phosphate. So that there's no confusion, and otherwise there would be a lot. Like I said, every cell chemistry has a different cell voltage, so we're going to keep it a little more simple, and we're going to use lithium iron phosphate. The next question, how many? Well, in order to answer that question, we're going to have to look at this information. So the nominal voltage of a lithium iron phosphate cell is 3.3 volts. Minimum voltage. Well, you never want to discharge it below 2.5 volts. That's the absolute minimum. And we typically design our systems to shut off above that. And then maximum charge to voltage, we charge to a maximum voltage of 3.5 volts. Now, if you were to charge to 3.6 volts versus the 3.5, you're not going to get any more range. Not a mile, not a quarter of a mile. All you do is you shorten the life cycles. This is the recommended charge to or maximum voltage per cell. So once we've established that information, we can go back and answer this question. How many? Well, it's going to depend on some other choices that you're going to make, and we're going to come back to this later on. Like I've said before, we kind of learn a little something, and we move forward, we come back, and we learn a little bit more about that previous topic. So, how many cells can be dictated by a lot of different things. Your traction pack voltage can be based on space available, payload capacity of the vehicle. We're going to discuss that. I think we already discussed that in the previous episode. And controller input voltage. And so the controller input voltage is going to be dictated by that motor controller combination that you choose. So, and we're going to get into motors and controllers down the road a little bit. But for now, we're just going to take a hypothetical scenario here, and we're going to say that our maximum controller input is 130 volts. Okay? This is strictly for the sake of discussion. Now, if we have a maximum input voltage to our controller, and I'm going to use the word controller inverter interchangeably. When we get there and we're talking about these things, you'll notice that in my mind, technically it's a DC controller and it's an AC inverter, but even the manufacturers, the AC inverters, they call them controllers because they do more than just invert. So anyway, we're going to use the generic term now, controller. It can be AC or DC. So anyway, maximum controller, that's the maximum amount of voltage that this controller will accept. And so, how many cells can we use? Well, again, part of it would be how are they wired, right? Well, let's make the assumption right now that they're in series. And remember, cells in series, the voltage adds. So, the voltage that you hear most commonly when people refer to cells, battery packs, everything else, they normally refer to the nominal voltage. And we will use the nominal voltage in calculating range, which is something we'll get into later on also. But for figuring the maximum number of cells, we're going to use our maximum input and we're going to use the maximum charge to voltage. So in this case, we would take 130 volts and we're going to divide that by 3.5 volts. And that would give us the maximum number of cells that we could use in this scenario. So if we do the math, we see that the answer would be 37.14, and 0.14 of a cell doesn't work for us, so the answer would be 37 cells. And 37 cells then would give us a maximum voltage and then nominal and minimum. 37 times 3.5 volts, our maximum pack voltage would be 129.5 volts. The nominal voltage, 3.3 volts per cell times 37 cells, it's 121.1 volts. And our minimum voltage, which would be 37 cells times 2.5 volts per cell, is 92.5 volts per cell. 92.5 volts for the pack. So this is our pack range, okay? Can't exceed that or that. So knowing that information, we know that, we have to have an inverter that, fit that range, which if it has a maximum of that, it should. Our DC to DC converter needs to be compatible with that range, and everything else. Our charger, everything has to be compatible with that voltage range from 92.5 to 129.5. So say you had an AC system that was okay with that upper limit, but say it cut out at 100 volts. It was good for 100 volts to 150 volts. Well, when you got down below 100 volts, your AC would shut off. So all your components need to be compatible, all your traction pack voltage components need to be compatible with that voltage range. The other aspect in all of this is not just the number of cells, but the size of cell, the capacity of the cell. Remember we talked about that before, previous episode. Just for discussion's sake, and say that we have a battery pack, it's 37 cells. The nominal voltage was 121.1 volts. And we're going to run a couple different scenarios. Let's do this one where the cells are 100 amp hours each. Okay? And what we're doing is we're going to see what that gives us as far as the capacity, okay, the storage capacity. How much power do we have available in that pack? And remember, power is equal to volts times amps. So we're going to take, for doing the capacity, we take the nominal voltage and so remember we got that multiplying the cells times the nominal voltage cells, 3.3 volts times 37 gave us this 121.1 volts times 100 amp hours gives us watt hours of 12,110 watt hours. Or expressed another way, 12.1 kilowatt hours. Okay, so that's our battery pack if we used 37 100 amp hour cells. Now, let's look at it if we used a 230 amp hour cell. Okay, so the voltage doesn't change. We still have 121.1 volts, but what's going to change are the watt hours. So that's 27,853 watt hours, or again, we could say that's 27.9 kilowatt hours. Now, later on, I'm not going to do that now, but later on, we'll see how this all comes together in the big picture. So you can see that using the same voltage, same number of cells in our battery pack, but varying the size, of course, is going to increase our capacity, our storage capacity. And we'll look at how this affects the range. And it's not just, you know, if we use a 200 amp hour cell versus a 100 amp hour cell, that we're going to have double the range. It doesn't work that way, because the 200 amp hour cell is going to weigh more. And you'll see the relationship between weight and range as we go forward. But here's the other thing that we need to be aware of, and that is, it's not only the capacity in total amount of watt hours available to consume, but there's also the discharge capability. And so if you've ever looked at specs for cells, you'll see that they have what they call a C rating. Okay, so they'll say that it can discharge at 2C, or it can charge at 1C, or maybe it has a continuous discharge of 3C. Well, all that's fine and dandy, but if you don't know what it means. So C is simply the short way they say capacity. So when they say a cell has a discharge rate of 2C, that means it's 2 times the capacity. And here's the capacity, 100 amp hours. So this would equal 200 amps. That would be this one would be 100 amps. This would be 300 amps. So, which one of these you could use in your project is going to depend on the rest of the project. Your motor and inverter, okay? Those being the main consumers. What is the draw? So if you have a 1,000 amp controller, so a 1 kilowatt controller, and if you were using a cell that had, and I talked about some of those prepackaged lithium batteries before, a lot of them are rated at 1C. Well, if you got a controller that can pull 1,000 amps, you're not going to use a battery that can only deliver 100 amps. You following me here? And so, and even one at 3C, that would be, 3. And then there's, when we're talking about this, ratings, there's going to be different ratings. And so they're going to have a continuous, typically, and they're going to have a maximum. So you can have a continuous rating and a maximum rating. So, like cells we use, continuous rating typically is 3C, and maximum is 10C. And this is for like 10 to 30 seconds. So if you're using a cell that's 100 amp hours and has a 3C continuous, that'd be 300. It could deliver that 1,000 amps, but it's probably not the best match, okay? It just depends on the vehicle this is in also. Again, everything's interrelated. We're just kind of touching on some of the things. We'll come back to this. So in this case, if you had a 230 amp that had the same 3C continuous rating, we can see that at 3C, instead of being 300 amps, this one would then be 690 amps, and that's continuous. Okay, with a maximum of over 2,000. So I would feel more comfortable designing a system that used these cells with this kind of controller. But like I said, when we get to controllers and motors, we'll come back to this. Another way to increase the discharge capacity of a cell is you could take 2 of the 100 amp hours, or you can take 37, and you take another 37, okay? So you have 2 strings, so you have 37 cells in series, and another 37 cells in series, and those 2 are in parallel. And what that does is that gives you double the amp hours. If you remember back to the little circuit we looked at in a previous episode. So now you have 200 amp hour of capacity, so you doubled the capacity, but we also doubled the current delivery capability. okay? Because each one of these strings would be able to handle 300 continuous. So now it could handle 600 continuous if you have the 37 in series and in parallel. I know I told you just a few minutes ago that we're just going to talk about lithium iron phosphate from here on out. We're going to deviate from that for a moment just to give you another example of a series parallel arrangement. And we're going to use the Tesla Model S module as an example. 444 cells, 74 in parallel, 6 in series. So 74 parallel strings of 6. The nominal voltage per cell, you can see this is not lithium iron phosphate chemistry, it's 3.8 volts per cell, which makes the module have 22.8 volts. The charge to voltage, 4.2 volts per cell, 25.2 volts for the module. Minimum voltage, 3.3 volts per cell, 19.8 volts for the module. Maximum discharge current is 750 amps for 10 seconds. One series string, 3.8 volts, nominal voltage, times 6 in series gives us that 22.8 volts. 74 series strings in parallel, you still have the 22.8 volts, and these are 232 amp hours at that point when you have that many in parallel, and it's that module is 5.3 kilowatt hours. Okay, and so if you needed, to get to that 130 volts, we're going to need more than one module. So in order to figure out how many modules, remember we had that 130 volts maximum. We're going to relate back that previous example, and we're going to divide that by the 25.2 volts per module, and that's going to come out to 5 modules. And the 5 modules then are that, so times 5 will give us the total capacity. And so our total capacity would be 26.5 kilowatt hours. Okay? And we're going to come back to all this kind of stuff when we talk about range and other things. Okay. We're going to talk a little bit about cell temperatures. And like I said, we're mainly focused on lithium iron phosphate. Its operating temperature is -4 to 149 degrees Fahrenheit. It will operate in that temperature comfortably. That's its operating temperature range. And I'm going to add a few tidbits in here. And one of the things that we hear about when dealing with different chemistries, or lithium in general, is thermal runaway. And the lithium iron phosphate chemistry is very safe because it has a very high thermal threshold. And so the cause of thermal runaway can be several different things, but let me explain briefly what is thermal runaway. Thermal runaway is a process which is accelerated by increased temperature, in turn releasing energy that further increases the temperature. So it just, keeps increasing, thus the term runaway. And causes of thermal runaway can be overcharging, overheating due to excessively high discharge rates, and damage to the cells. But here's the big difference, and you can see here in a second. Some cells are much more stable than others. That's why I said all along, key is chemistry. Chemistry dictates voltage, but it also dictates its behavior and its safety factor. So this is the thermal runaway, or the thermal threshold, I should say, for lithium cobalt oxide. The thermal threshold is 302 degrees Fahrenheit. NMC, which is manganese cobalt oxide, or nickel metal cobalt, they're 334 degrees Fahrenheit. And compare that with the LiPo4s, which is 512 degrees Fahrenheit. So you can see this can get much hotter before it becomes, thermally unstable. Gets to that thermal threshold. So, like I said, one of the main reasons, or reasons we choose this is the safety aspect of the chemistry. Now, I mentioned briefly before battery cycle life, which is the total number of times the cell can be charged, or discharged and recharged. And so we're gonna, the LiPo4 chemistry. Typically, when they discuss its number of life cycles, what they're referring to is the number of times that you can, discharge this thing down to 20% of its total capacity. Or another way that they'll describe that is depth of discharge of 80%. So they've removed 80% of its capacity, which means you have 20% remaining. But they'll do that. They'll discharge it to a depth of discharge of 80%, charge it back up, discharge it to the same level again, and back and back. That's life cycles. And there's two things that really affect life cycles. One is the depth of discharge, and the other is the rate of discharge. And by rate of discharge, I mean, are you pulling, 100 amps out of it, or are you pulling 1,000 amps out of it? So the faster you're discharging that, the greater amount of current you're pulling out at any given time. That and how far you discharge this greatly affect your life cycles. And as an example, they're rating it at whatever, at 80%. Well, if you only discharge it to 50%, you don't exceed 50% depth of discharge, you get 1.5 to 2 times the life cycles. And if you only do it at 20% or less, they don't even have a number. The things that I've made a big deal about, and that's safety. And I'll touch a little bit more on that right now. A lithium cell, I don't care what the chemistry is, has a huge amount of potential. Lithium iron phosphate cells, like I said, nominal voltage 3.3 volts, but it can discharge 2,000 volts for several minutes. And there are people that have done that and tested that. That's how I know. Huge amount of potential. So if you're working around them and you short it with a piece of jewelry or a screwdriver, a wrench, or something by accident, it has a huge amount of potential. Whatever lands on that, depending on the size, it's either going to get white hot real quick or it's going to vaporize it. Huge amount of potential. So you need to treat these things with respect. Just like that, outlet on the wall. We don't even give it a second thought. It has a huge amount of potential, and if you don't handle it in the way that it's intended to be handled, it can kill you. And so one of these cells could definitely injure you seriously and permanently if you don't give it the respect it's due. A couple other things about cells that we'll touch on at this point, and that is kind of going off that list we had earlier. And one is the care for the cells. So it's real important that you keep your cells clean and dry. And so, factory produced cells, they're in a containment that is sealed, and those cells are protected from the environment. I see a lot of people that do conversions and their cells really aren't contained very well, specifically for an accident, but also for the elements. And I've seen firsthand that people live in like a coastal area where they have a lot of moisture in the air, a lot of salt in the air, and these cells aren't properly contained, where they get a lot of the moisture and so forth, and you can actually have paths to ground, which can lead to frame shorts, and we'll talk about those later on too. But it can also cause discharge to your cells. They're leaking a little bit all the time. And then another big one is the interconnects. You want to make sure that your interconnects are tight. So if you're using like prismatic cells, like I showed you, where you're going to have a interconnect between each cell, or however you're doing yours, it's very important that those interconnects be tight, because if you have a loose interconnect or a loose connection anywhere, not just with the cells, it causes resistance, and resistance causes heat, and you'll have a problem. In our next episode, we're going to talk about several things like we do each episode, but a few of the things we're going to talk about will be cell management, cell monitoring, and cell balancing. So I hope you join me. And in the meantime, if you're here, you watch the video, click the subscribe button, click the notification bell, and I hope you liked it. If you did, hit the like button, and I really hope we'll see you next week.